В прошлый раз, видимо, не было, потому что они не создали эту трансляцию.
Да, это что-то. Ну, какой круг? С какого-то момента туда пошла. Да, пошла.
Okay, so we almost finished chapter 3, which is about localizing subcategories, localization functors, or for shortness of just localizations, and also homotopy limits and colimits. I just want to, last time we discussed a situation where homotopy colimits actually coincide with the colimits in the category of complexes, and today I want to formulate something kind of dual for the limits, and essentially I'm going to leave everything as an exercise, because if you understand one proof for the colimits that I've done last time, you can kind of dualize everything. Okay, so let me assume that A in this short section, so let A be a complete abelian category, and I have some inverse system, so I'm going to call this E. So this is just a functor from the opposite of the natural numbers to the A, or more directly, inverse system. So directly this is just a sequence of objects and maps parameterized by natural numbers. Okay, so in this case, we, as usual, well, as we've done for the when we discussed homotopical limits or dual when we discussed homotopical limits and dual when we discussed colimits, we can introduce the map from the product of all these objects. So call this new, into the product, and so this product of all natural numbers. So here for the products you have projections, so to the Pn, and here you consider a map which is mu n plus 1, Pn plus 1. So this is a definition of the mu. So mu, you can specify a map to the product if you know compositions with the projections, and the compositions with the projections is mu with the shifted index, and the projection with the shifted index. Okay, so in this case, if I consider the kernel of the map 1 minus mu, then this is, well, by the well-known theorem from the standard category theory, this is the inverse limit of this sequence. Well, potentially there is also a colimit, but I want to consider situations. So I have this kernel. So if I suppose that this is epimorphism, then I get a short exact sequence like this: 0, inverse limit, product 1 minus mu, product 0. Right? So this is, if this makes sense, if 1 minus mu is epi. Right? So, but then if I have such short exact sequence, there is a distinguished triangle in the derived category, which is inverse limit, product, and then inverse limit shifted. Right, so this is a distinguished triangle. But if this is a distinguished triangle, right, if you go back to the definition that was, I think, at the end of the lecture 2 weeks ago, you can identify this with the homotopy colimit of the Pn. So some special, is it, so homotopy limit, sorry, some homotopy limit, not colimit. Right, so the idea is that in some cases, well, the computation, so what's the problem? Computing homotopy limit just by definition might be quite hard. But if you can identify this with a limit, well, for the ordinary limit, you might know some examples where you can compute this explicitly. Like, for example, you know that if you can take some kind of truncations, and you know that in this case, the inverse limit of truncations is just a given complex. So this is kind of simplification, and what I want to know is when this is actually true. So this is why I'm interested in this question. It's kind of a technical tool to compute homotopy limits, like just computing it to inverse limits. And there is a lemma, which will be an exercise. So with two parts. First, if A has a family of projective generators, additionally, I assume that the maps in the inverse system mu n, they are all epimorphisms, so this is not epi, for all sufficiently large indices n, so for all n sufficiently large.
What is projective generators? Is generators the projective?
Exactly, yes. So then we have the right conclusion that the map 1 minus mu is epi. So this is one situation. Of course, you can say this is some kind of limited situation. For example, that's something that doesn't work in algebraic geometry. That works, for example, in the category of modules over a ring. There we have a projective generator, but not in the algebraic geometry. So 2, which is actually, if you think about this, quite very easy exercise. So maybe in the first you need to do something. It's not a completely trivial statement, but for the 2 it's more or less straightforward. So I assume that mu n is split epi, and this is for every n natural number. Then the conclusion is that 1 minus mu is split epi. In particular, this is epi, so this argument identifying limits and colimits works. So this will be an exercise. So as you can notice, that this is just a statement for abelian category, and I want a statement for the category of the complexes. So I need to restate this. So I need to restate this and assume the following. So let A be a complete abelian category and have an inverse system P. So this is for the opposite to natural numbers. So that's an inverse system of complexes to the C of A. So the generalization is corollary straightforward because, well, for example, in the part A, I'm going to assume that so if A has a projective generator, right? And if I assume that the A category A has a projective generator, and we want to apply lemma with the first part to the category C of A, right? I know that in the category C of A, I have a family of projective generators. Then I can take this projective generator and put it in all possible degrees. Right, it's always a countable family parameterized by integer numbers of projective generators in the category C of A. So projective generator assumption is the same as before. The second assumption is the same as before. Mu n is epi for all sufficiently large indices. So, and the evolution is the same as before. So then, smell is epimorphism. And condition 2 is kind of trivial, and straightforward generalization of the lemma. Where you just, well, you need, for example, to have a complete category, but if A is complete, then the category complex is also complete, because you can take limits kind of termwise on all level complexes. So if is semi-split, of all indices, so then 1 minus mu is semi-split. Okay, so just a bunch of observations about the abelian categories. So again, this exercise. And I think actually more or less I solved the first part of the exercise, and the second part follows immediately. So I can erase exercise and say this is clear if you solve that exercise.
Excuse me, what is semi-split?
Well, it means that you have an epimorphism, right? And you have a map in the other direction, such that the composition is identity, but the map in the other direction is not a map of complexes, it's only a map of graded objects. So the map in the other direction, you have the map in each level, but this map doesn't commute with the differential. Okay. So the last thing that I want to discuss in this chapter, or in this last section of this chapter, so general homotopy limits in the derived category of an abelian category. So maybe I repeat this general idea one more time. So if you have just a generated category, you can define notion of homotopy limit only for special kind of diagrams, namely the sequence parameterized by natural numbers. And the applications you kind of want to consider all possible directed diagrams, right? And that's not possible to do in any generated category, because if you just assume that you have a generated category, it's not enough homotopy information in this category. But if you do this in the derived category, then we can actually work with the complexes, and then just work with the complexes up to quasi-isomorphism, and you can compute something in the category of complexes, which is again an abelian category. Okay, so the assumption here is the following. I assume that A is co-complete, abelian category. So G now will be some directed system for a directed set phi. Directed system. Well, and then I can do the following. I can give you the straightforward definition that the homotopy colimit in the derived category. Well, I wrote this in the category of complexes, but I can just as well consider the derived category. The objects are the same, so this will be a bunch of objects and the mass between them. It makes sense in both categories. So the definition of the homotopy colimit is the following. I take the totalization of the homological Roos complex of the G, where I think about C of A as the abelian category, and in the abelian category I can compute the homological Roos complex for the colimits where I need homological version. So this is a dualization of what we discussed last lecture, but I think we can dualize this straightforwardly. You just can inverse all the maps. But I want to, and since kind of the objects in this category are complexes, So the homological Rus complex will be a complex of complexes, so double complex, and then I take this totalization. That's the definition. That's a kind of standard definition of what you consider homotopical limit in the derived category. And we also can explicitly rewrite this, what this definition means. So what's exactly the bicomplex, what are the maps in this totalization. So for this I want to introduce notation. So I want to rewrite this definition with all the precise information and erase this Rus and write everything explicitly. So for this I fix notation. So I'm going to call WK. So the chains of the category I of length K. So in other words, this is just something like, maybe, well, somehow I switch notation. Let me call this I to the K. Well, because the objects I want to denote, so this I to the K, so this is the set of the I0, which is less than I1, less than less than IK. So that's the chain of the maps of the length K in the category I, just a notation. So then I can talk about the Rus bicomplex, and the Rus bicomplex with the position K and J. So notice that this is a homological Rus complex, so one of the differentials decrease degree by 1, so one of the differentials is degree -1. And I want to construct a homological object, so I kind of need to inverse the indices. So that's the explanation why, for example, I want to define it like this. I want to say that this is by definition 0, well, not by definition, but really by this definition. So if K is positive, but in the negative degrees, I have G, I naught, J, where I is in the I to the K, and this is if K is negative or non-positive. Sorry, there is a small mistake here. This is, of course, has to be I to the minus K, right? Because now in the second option K is non-positive, so it makes sense this I need to write I to the minus K. That's essentially this minuses and comes from the fact that this is homological, and on by hand, by inverting all the positions K to the minus K, I make it homological. So does this definition make sense, especially the second line?
What is I0?
Well, you have this, so you have I, which is in these chains, right?
Mm-hmm.
And I0 always the element in the first position.
Mm-hmm.
So it's exactly this notation that I used in this definition. And so this will be an object with the index I0, and this sense this is a complex, there is second index J.
And this is the element of Rus complex, yeah?
Yeah, that if you kind of look at the definition of the homological Rus complex, dualize everything, and just apply this definition for the diagram of complexes, this is what you get. And also, since this is homological, again, I'll get differential degree -1, and I want my differential to be degree +1, so that's why I need to kind of put this in the negative positions, right? Because the homological complex will be from 0 in something in positive direction.
So we like constructed cohomological Rus complex from homological Rus complex.
No, it's really homological Rus complex, but this is kind of trivial duality in homological algebra. Every kind of chain complex you can consider as a cochain complex if you just inverse all indices to the minus indices. Mm-hmm. So this is what I do here. If you just do this by definition, you'll get something that sits in the for the K in the positive degrees homologically, but you can also put this in negative degrees cohomologically.
Mm-hmm. Do you define the Rus this Fukalim in DA if we maps I to D or only in C?
Well, really, the way this is written, this is in the CA. right? Essentially the definition is the following: you start with some directed system.
Yes.
Well, you suppose that this is a directed system. Well, if this is in the DA, you kind of lift this to the complexes, right? If this is even in the CA, you get the directed system, and then you just explicitly give you a bicomplex, and the totalization of this bicomplex is by definition the homotopic limit.
So if you are given G from I to D, we need to lift it to C.
Yeah, how
Yeah.
we can
Oh, if you can
Yes,
to do this, well, it's in general. If you just have two arbitrary complexes, the map is just given by some roof,
yeah.
and it's not clear how to do this. But when we develop this theory of derived categories, we will notice that the derived categories can be interpreted as a homotopic categories of some complex with some special properties. So to really, instead of DA, we'll work with the homotopic category. And in the homotopic category, I think you can lift this kind of by taking resolution. So essentially you have this diagram in the category of complexes. For each term, you take the appropriate resolution, and then you lift this map to the map of resolutions. And then you get a directed system in the homotopic category of resolutions. But at the moment, since we didn't discuss any resolutions in general, you can think about this just as a situation in the CA. That's enough. Because essentially I just want to describe this complex. Okay, so that's a definition kind of the terms of the Roos complex, and I also need to define differentials. To define differentials, let me fix notation for the canonical injections. Right, since this is defined as a coproduct, automatically I'll get canonical injections, which will be parameterized by the index j, which is just an integer, and this I, which is really a chain of length k. So, and this is mapped from the G I naught J to the Roos G Kj. So this is canonical injections of the coordinates.
So I here is a chain and J is a number.
Yeah. So I don't know, it's a little bit unfortunate notation. Maybe I need to do something like underline this I to know, emphasize that this is not really a number, that this is a chain in the category I of the landscape. So then I define the differential, the two differentials. So there is differential d1 from the position in the bicomplex with indices k and j. And so let me just write where this is. So this is from the Roos G, K, J to the Roos of G, K plus 1, J. And this is defined as an alternating sum. So D, sorry, this, well, I don't know. Yeah, so this D1 well, maybe I just write the formula of the alternating sum. So D1 with the indices K and J. If I want to specify this map, it's enough to specify this map when I take a composition with the canonical injection. Right? So, and for this thing, I can write a formula. So this will be the U, J, and the chain is from I1 to the I with the minus K. Composition between U, J, I0, I1 plus the sum, so over some index L between 1 and minus K. So this is minus 1 to the L. And here you just have the canonical injections with the appropriate low index. So you take this chain, which starts with I0, and in this chain, when you reach I with index L, you just omit this element in the chain. And hence you'll get the chain of the length K plus 1. That's what you get if you just take a definition of the Rus chronological complex and plug in the, instead of objects, the complexes of objects. We can essentially see that J in this whole story is just a fixed index.
What is mu?
Hmm?
What is mu?
This is the map that I suppose that I have in the directed system. So I have G, I, or maybe better K and L. So G, L, this is mu, K, L. So these are maps in the directed system. Okay, and the second differential, this is much easier to define. So this is dk with the indices k and j. This will be from the, again, from the roots of g, k, j to the roots of g, k, j plus 1. So the second differential, the vertical differential.
Yeah, and why we, in this formula, get something in roots j, k plus 1 j? Shouldn't be k plus 1 j's.
K plus 1 what?
Well, shouldn't we get something that that lies in chains of I of length k plus 1? And did you get it?
No, what we'll get is something that lives here, right?
Yes, and it's there is I index lies in chains of length k plus 1.
Yes.
And there's, I don't actually see, there's from I1 to I minus k, it's look like it's a chain of length k, isn't it? And there's also its chains of length k.
Well, no, you essentially, well, if you have doubts that this is a correct formula, you can think about this way. So you have this map, right?
Mm-hmm.
So here you have the canonical embeddings, which is essentially given by these maps, right? So now I have a canonical embedding, say which is given by this, right? So to define, so
Minus 1. Как будто k minus 1.
We have chains of length k, we have k plus 1 vertices.
Yes, and there is I1 to I minus k, it's just
So-
k.
No, it has k vertices.
And should,
Minus k, so it is a chain of length k.
oh, it goes like 1, 0, minus 1, and to the minus k?
No, minus k is positive.
Aha, so then it's just chains of length k minus 1.
No, e minus k minus 1.
Yeah.
And because
Minus
k is
k
negative.
minus 1, yes, that's true. And that's what I should.
And it is minus k plus 1.
Ah, okay. Fine, thanks.
yeah, but you can definitely work out the details if you, as I said, write the corresponding co-injections, write this map, and you see that this actually makes sense. Yeah, I agree that the definition is a little bit annoying with all this and the notation with the chains. Yeah, so what I was trying to say that for the second differential, which is the vertical differential, the situation is much easier because there you just need the differentials in the complexes J that are given. So D2 Kj. This is just by definition the direct sum of the differentials. In the complexes, so this is for a non-positive, and otherwise this is just 0. So, well, this is really just a kind of explicitly writing what the Rus complex is. Well, you need to check that, of course, in this case, d1 squared is equal to 0, d2 squared is equal to 0. For d2, this is more kind of obvious. For d1, this is the same computation as for the Roost complex, but anyway, I skip this computation for the Roost complex, so again, exercise. And also d1, d2 is d2, d1. So that's something that I leave to you to verify. Okay. Okay, so now let me formulate lemma. So let A be a Grothendieck category. Grothendieck category. So then the localizing subcategory of the A coincide with the whole derived category. Okay. Is it clear what the statement means? So I have derived category. Inside this derived category, I have just an abelian category A. I'll consider this as a class of objects. And I look at the smallest localizing subcategory containing all the objects in the abelian category. That's the loc of A. And in fact, this is as huge as possible. Namely, this is the derived category itself. Okay.
So we find the smallest localizing subcategory containing in DA.
You can repeat this?
We find the smallest.
Yeah, the smallest localizing subcategory in the DA containing all the objects from the A. So the proof is kind of by a couple of reductions. So this, maybe I even separate this into two steps. So maybe step one, that in this step one, I can show that every bounded complex is in the log A. So I want to show that every complex in the log A. First I show that every bounded, I mean bounded on the both sides. And this is just a simple inductive observation, right? Because if I have a complex, let me call this maybe A, which is kind of different font than the category A. So A is a complex, and to indicate this is a complex, I also want to write dot. And this is bounded complex. So A with a dot. So let me write this as follows. So I have zeros everywhere, then I'll get some finite part, A0, A1, up to some AN, and then after that I'll get zeros. So that's a bounded complex. Without loss of generality, I can assume that it lives in the degrees of 0 and m, otherwise I can just shift this. And then I can look at the complex, which I'm going to call A prime, which is really just the same complex from which I erase the A0 term. Right? And then the differential, so let's solve the differentials in D0, D1, etc. in this complex. So then I can look at the following situation. I take object A0 as an object in the derived category. I have a map to the complex A with a prime, and this map is just the differential D0. Right? What happens if I take this map and try to complete this to a distinguished triangle?
So how this map works? It's from A0 to A1?
Yeah. Yeah, so you have this complex, but maybe I can write it here. So there is also A0, and there is a differential D0.
Yeah, and A0 is not a complex, it's just an object, okay.
Yes, yeah. That's just as a complex that this in only one position, and or in other positions this is 0. You can notice indeed this is a map of complexes because here you have 0, so commutativity of this square just means that the composition of two differentials is 0.
Yeah, the thing that I don't understand is A prime has A1 on the zeros degree.
Well, shift it though in such a way that this makes sense. So I want A0, say, in the position not 0, but in the position 1. So I need to shift this by -1.
Mm-hmm.
Maybe minus 1, right? Okay, maybe I just erase this, there's no space to continue the computation. So A0, which I want to put in degree, say 1, so minus 1. There's a map with by the differential to the A prime. Right? And I was asking what happens if I complete this to distinguish triangle. In other words, I would just take the cone, right? So we know that distinguished triangles in the direct category are obtained by taking the cone of this map. If you do this, you just by definition of the cone get this complex. So this will be A0 dot A0. So by induction, for example, if you
Why again this complex?
this complex,
Yes.
this you just look at the definition of the cone and plug in here this complex and this complex.
Do we think that something is exact here, or it is? These are arbitrary complexes.
No, this is just a complex of kind of finite lengths bounded.
Yes.
And for any complex which is bounded, you can do this computation and present this as a cone of the complex which is of smaller lengths and just an object in the category. So you do this by induction. So of course the base of the induction is kind of given, right? So all objects which are complexes of with one object, this is already here, and now you assume that you have this that this is true for the complexes of lengths, say n minus 1, which is this complex. So since this is triangulated subcategory, so this is there, hence this complex is also there. And that's the proof of the step 1. And the step 2, which is based on the computation with the truncations that we've done on the previous lecture. And it says the following, that if you, well, essentially the step 2 is the finish of the proof. So block A is the dA. You take a complex, say again, A. So that's some object in the direct category. So then, since this is a complex, you can write this A as the whole limit of the truncations on both sides, so minus n plus 1. So that is something that I noticed a week ago, that you can use this kind of double truncations, and then we can write this as a homotopy colimit of the same truncations, A minus n plus 1. And this is because the conditions that we discussed at the end of the previous lecture, when you can identify, so today we started when we can identify limits and homotopy colimits. There was a kind of dual discussion for the colimits and homotopy colimits, and you can notice that the maps in this directed system are satisfying the conditions of the lemma that was at the end of the previous lecture. Namely, these maps are split monos. Hence, limits can be identified with homotopy limits. But the homotopy colimit of the objects which are in the localizing subcategory are, of course, in the localizing subcategory. Yeah, that's the end of the proof. Does it make sense? We presented this as a homotopy colimit of the objects that we already know in the localizing category. And if you take the homotopy colimit of something which is already in the localizing category, we'll get something in the localizing category. Because you have the distinguished triangle that defines homotopy colimit, the two terms which are co-products are in the loc by definition.
When did we use it as indicated in this isomorphisms?
Yeah, so to go from the collimate to the homotopy collimate, this was the assumption is used.
Yeah, so when we say that Hochkolin lies in localization category, we say that products of objects that
yes.
lies in localization category, and then we just take code.
No, I'm not sure that I understood what you said, but that sounds almost correct. So for the homotopy collimate, you have a distinguished train, which is the definition of homotopy collimate. And the other two terms in this distinguished train are coproducts. And the coproducts are in the log by definition because log is closed on the coproducts. So hence the third vertex is also in the log since this is strangulated subcategory. Okay, so second lemma. Yeah, and I think that actually the condition that this is Grothendieck category is essential, and you can drop this. So if you take just any abelian category, it may be nice enough, but well, say AB4, but not AB5. I'm not sure that this is the correct statement. Essentially, because of this isomorphism. Okay. Yeah. So, but if this is not the Grothendieck category, you don't know the exactness of this collimate, and that's a problem. So it might be something like you need to left to right of this collimate. So you might get some variation, but I'm not sure that the statement itself is correct without any corrections. Okay, so let's assume that I have a Grothendieck category. And suppose I have two triangulated functors, so and S and T. So these are functors from the derived category of A to some other triangulated category. So these are coproduct preserving triangulated functors. And I assume that so if I have a trinatural transformation, let's call this psi. So if psi, say from the S to the T, is a trinatural transformation, so with the property that if you look at the component of this trinatural transformation for an object A, then this is an isomorphism from the S of A to the T of A. This is for any object A in the category A.
And it's not natural isomorphism. It's not natural isomorphism.
No, it is. It is
natural isomorphism.
It is given as a natural transformation, but if you look at the components which are kind of parameterized by the object in the abelian category, you know that these are isomorphisms, all of them. They are natural if you in this special case where you take say A and B, which are both from the abelian category.
It's from abelian only.
Yeah. So only from abelian. So then the conclusion is, of course, that this is actually a natural isomorphism. So then, psi is natural isomorphism. So it's only enough to check that you have isomorphisms for the objects in the abelian category. So I want to say this immediately follows from the previous lemma by the following observation or computation. So let C be a triangulated subcategory in the derived category. So this is whole subcategory. subcategory on which psi sub x is isomorphism. So x is an object in C. Right? So at least we know that A is in the C. This is given in the condition. But also, since these two functors are coproduct preserving, so if you have this for an object, this isomorphism, we also have this for the coproducts. And so what I want to say is that then the log of A is contained in this C. So A is contained in this C, and this category C is closed under coproducts by this condition, and it's also closed by taking it's also generated subcategory, because if you have isomorphism of two terms, you have isomorphism of the third term also. But this log A is just the whole derived category. So C is actually D of A. So finally, the last theorem of this section and also of this chapter, well, they will be a little corollary without a proof, but anyway. So let A be a Grothendieck category. So then, homotopy co-limit of a diagram inside with co-limit, co-limit which is just a direct limit. Or maybe I write this co-limit, I'm not sure. Well, maybe I write just as a co-limit to have similar notation. Coincide with the co-limit. Well, coincide mean quasi-isomorphic. Quasi-isomorphic to co-limit of the diagram. So this is something that we already know in the special cases. We know that this is true if you have a sequence. So this diagram that we consider is just a sequence of natural numbers, but this is true for any diagram.
And this co-calling and calling in D of A.
The homotopy co-limit is exactly as I defined 10 minutes ago.
So it's in D of A.
Well, it's a priori in the C of A, but if you work a little bit, you can interpret this as a D of A. Essentially, I'm saying the statement about the complexes. You have a diagram of complexes. You can take the homotopy co-limit as I just defined, or you can just take the honest co-limit in the abelian category of complexes. The two answers are quasi-isomorphic.
What is the diagram? We have directed.
That's the directed system. So that's the diagram is what I before or something like this.
And what is Hokalim for this diagram?
Yeah, that's something that I defined 15 minutes ago.
Totalization of
Yes.
yes.
Okay, so the proof follows by the previous lemma, since we have, let's say, trinatural transformation psi from the homotopy co-limit to the functor co-limit, right? So this is because we always have this in any abelian category, particularly the abelian category of complexes, a map from the Roos complex, homological Roos complex, to the co-limits. Because it will be if you just write the definition of a Roos complex, the co-kernel of the first differential will be exactly the co-limit, and that's the standard formula that you can compute co-limits as the co-equalizers of the co-products. So that's the natural transformation that we always have. And so I want to say that clearly both functors are preserving co-products and if you have some object in the abelian category, so if the diagram G is actually a diagram in the abelian category, not the category of complexes, then psi with the index G, so this is a map from the Roos complex, homological Roos complex of G to the co-limit. And this is isomorphism. Right, so I've done this computation for a little bit actually more general computation with the Roos homological complex and derived limits. That was true that we saw this last time. You can dualize everything and get this conclusion, but this is a little bit better because there is no left-right functor, since I assume that the category is Grothendieck, so co-limit is an exact functor. Right? So you compare these two triangulated functors, you notice that they coincide on the abelian category by the dualization of computation, dualization and actually simplification of the computation from the previous lecture, and then you use the lemma. Yeah, by the way, maybe you have a question why co-limit is a functor on the derived category, it says triangulate functor. Well, the reason is that this is just an exact functor. Exact functor automatically extends to the triangulate category because it preserves acyclic complex or quasi-isomorphisms. So this is the reason why I want to work with the Grothendieck category, because here this is automatically exact, I don't need the right functor. So you may ask a question about the dualization, right? So there's definitely a dual situation when you consider homotopy limits in the derived category and limits just as in the complexes. But of course you can kind of dualize everything in a straightforward way, but then you get category such that the opposite category is Grothendieck. And that's not a very interesting condition from the point of view of applications, right? Because categories that we're interested in, like categories of sheaves on the topological spaces, modules in algebra over ring, or OX modules with quasi-coherent homology on the schemes, they all Grothendieck. They not do. Yeah, in this way this is useful and has applications for what we do. But you can kind of ask the more interesting question. You don't dualize this condition, you just ask what are reasonable conditions on the category A in such a way that you can write homotopy limit and the derived limit. So, and this can be done. So if you want to dualize this, you drop the assumption that this is Grothendieck, you modify what the assumptions you have. Well, for example, something like maybe enough projectives and AB4 star, and then under these assumptions you show that homotopy limits coincide with the derived limits. So that's, if I decided that this exercise is sufficiently doable, I'll probably add something like this to the second problem set. So, but anyways, from this theorem we have a corollary which says the following. So let A be a Grothendieck category. I have L in the derived category. So this is a localizing subcategory. Localizing subcategory. In other words, closed standard products. So, and G from I to the C of A. So this is a directed system of complexes. Such that if you look at any particular complex, G of I, so I So this is in the L of any I in the directed set I. So then the conclusion is that the colimit of G is in the localizing category. Of course, the proof is trivial, I don't really need to prove anything, right? Because I know that the colimit can be identified with the homotopy colimit, and localizing subcategory is closed on the homotopy colimits. So that's the statement that I announced before I've done this whole theory about the Roos complexes and homotopy colimits in the derived categories. And I still want to propose a challenge. Can you prove this corollary without theory of the homotopy colimits in the derived category? Because in the statement, there's really everything kind of naive and translative of derived category, localizing subcategory, so this makes sense. So can you prove that the filtered colimit also in the L? I don't know how to do this, and to do this, I need this theory of homotopy colimits and this identification. Okay. So that's the end of the chapter 3. And we still have 20 minutes, so I'm going to start chapter 4.
May I ask a question
Uh-huh.
about definition of focal limit using root complex?
Uh-huh.
So if I want to compute this homotopic limit for some directed system, should I replace it by some resolutions or not?
Well, I was saying that you can think about this as a directed system with the complexes, then you don't need to replace anything. But if you want to take a directed system in the derived category, right? So then in the derived category, you can get another directed system where you take each term, you replace this by the appropriate resolutions, a k-injective resolution, a k-projective resolution, and then the map. So you have two objects in the directed system, you have a map between them. You can leave this map to the resolutions, and then you get kind of directed system in the homotopy category, say, okay, injective complexes, okay, projective complexes, and this is again kind of honest directed system of complexes where you pressed everything by resolution. And since we didn't discuss these k-injective, k-projective, that's why I decided to skip this explanation.
Okay.
But the problem I'm trying to solve by this resolution is the following. If I just say that I have a directed system in the derived category, the maps are given by some proofs. And this theory of Roos complexes doesn't work with the Roos, because it's really theory for abelian categories. And I also want to make a historical comment. It's interesting that the Roos complexes were introduced in 1961, and essentially these Roos complexes are homotopy limits and colimits, but kind of if you consider this, it's a very elementary situation of the derived category of the abelian category. And the homotopy limits and colimits, let's say in algebraic topology, I think was introduced 11 years later by Bosveld and Kahn in 1972. So I think many people in topology don't realize that actually what they introduced was already known 10 years in homological before in homological algebra. Okay, I want to start chapter 4, which will be derived functors and resolutions. So this is the chapter in which we discuss k-injective, k-projective resolutions. Also, general properties of derived functors. And also, this is the chapter in which I'm going to show that if you take a derived category of the Grothendieck category, then the resulting category has home spaces which are just sets. So section 1 of this chapter is formal discussion of derived functors. So you might already know what are derived functors kind of in a more naive sense. When you take resolutions, you take partial derived functors. Here what I want to develop general theory of derived functors in triangulate categories, not just for derived categories. So essentially I'm going to solve problem have triangulate category functor with off. So let me formulate this maybe as a definition. So first definition. So let Q from some triangulate category the D mod C be very quotient. motions. So f is a functor from D to some other triangulate category T. So is a triangulated functor. So a right derived functor is a pair. I'm going to use notation RF for a functor, and also in this pair I have a natural transformation which I'm going to call beta. So the pair where the functor RF is a functor from the quotient D mod C to the T, and natural transformation, so beta is natural transformation from the functor f to the composition of the RF and Q. So this is natural transformation. So with the universal property, so this pair has a universal property. So universal property, which is the following. So for any other functor g from the quotient category D mod C to the T, and natural transformation, say rho, from the f to the g q. So there is a unique natural transformation. There is unique natural transformation eta from the RF to the G. So making triangle of functors and natural transformations. So in this triangle I have F, there is a natural transformation theta, which is to the RF composition with Q. So there is also functor rho, which is to the G composition with Q. And here I have natural transformation, which is eta recomposed with Q. So making the triangle commutative. That's the definition of a derived functor. Of course, as usual, something that is defined by universal property, we don't know whether this exists, but we know if this exists, it is unique, up to unique isomorphism. Okay, so let's continue. If we don't have questions, I'm going to add a new page. And maybe there are some kind of very easy statements, but I maybe skip them. So I understand the right derived functor is unique if it exists up to canonical trinatural transformation. Maybe I'll do the next definition and then prove something a little bit more interesting. So definition, a triangulated subcategory, category D. So in the category D is right adapted for the pair F and C if we have two conditions. So first condition is that the intersection of the C and A is contained in the kernel of the functor, and the condition 2 is that for any object X in the triangulate category D, there is a map F from the X to some object M with the property that the M is in the A and F. I have triangulate category, I have triangulate subcategory C, and I have some functor F from the D to some other category T. So essentially, for example, if you look at the condition 2 of this adaptability, it means the following. You can kind of look at the example. So suppose your category is the homotopy category, D, so D is the homotopy category, C is the subcategory of acyclic objects. So in this case, more C, this is the kind of morphisms which are quasi-isomorphisms. So this thing says that for any complex, there is a quasi-isomorphic complex from some subcategory. Yeah. So maybe it is helpful to keep this example in mind when the category is homotopy category, more C is the quasi-isomorphisms, and look at this theory that I'm going to present as a generalization of this situation. Okay, yeah, and okay, then to finish definition, and it's just another terminology. So a functor is called right adaptable if there is triangulated subcategory adapted for F and the subcategory C. So in other words, this is what helps you to compute derived functors explicitly using some resolutions. So this is the direction that we will go to. Okay, so first lemma. So let C in the D. Well, I have two subcategories. I have A and C. So let A and C in the D be triangulated subcategories. If at least one of the following conditions holds, so conditions are kind of dual to each other. So condition A and condition B. So condition A says the following, that for any and Y is in the subcategory A, there is morphism F from the X prime to the X with the property that the composition SF is in the more C, X prime is an A. Or dually, by inverting the arrows, for any T which is a morphism from Y to the X, which is the more C, Y is in the A. So there is morphism F from the X to the X prime with the properties that the composition F and S is in the more C and X prime is in the A. So what you can notice about these conditions is that, for example, if you assume the second condition of the adaptability, this implies, say, condition A of the lemma. So condition of the adaptability is a little bit stronger, but this is what we really need to prove the lemma. So what's the conclusion? So if one of these two conditions are true, then the canonical functor from the A quotient of the C intersect with A to the D mod C is fully faithful and also reflects triangles. Reflects distinguished triangles, which this second part I don't think they're going to use later. Okay.
This reflects.
Oh, this is the standard terminology in category theory. What it means that the functor reflects some property. Or, for example, what it means that the functor, say, reflects monomorphisms. It means that you have a map, you apply functor, and you get a monomorphism. Then you can conclude that the original map was a monomorphism. So here, if you have a triangle, which is just kind of 3 objects and 3 maps, you apply the functor, and you get a distinguished triangle, then it means that the original data was actually also a triangle. Okay. Just for shortness of the definition, I want to say that the C prime, so shortness of the notation, C prime is the intersection of the C and A here. So now I'm going to use universal property of the quotient, since I have the C prime, which sits in the kernel of the functor A is embedded into the D, and then there's a quotient to the D mod C, right? So clearly, by the definition of C prime, I have this embedding of this C prime is in the kernel. So there is functor little q, which is the following. So I have the embedding of A into the D. So here I have a canonical map to the A modulo C prime. So this is canonical map, canonical functor to the D mod C, and the functor Q is here. So that's the canonical functor that I have in mind when I say that there's a canonical functor in the statement of the theorem. So now I want to show that this is fully faithful. So, of course, these conditions are dual to each other, so it's enough to prove only one of the versions. So we're going to prove A. So assume condition A, and for B, the proof is dual. Okay. Now suppose I have, so this is fully faithful. It means I need to think about morphisms in the quotient categories. So suppose, yeah, and what I do with the morphisms. So suppose I have a roof that represents a morphism in the quotient. So say vertex W, X and Y. So this X and Y are just objects in the A, and this is a map. So in the A modulo C prime, right? So now I'm applying Q, right? What this Q is actually doing with this roof. Can you kind of compute the Q on this roof?
So it would be the same. It's just W, X, Y. And
It's exactly the same thing, but you kind of, if you formally write something like an embedding here, right? You kind of applying this embedding to this triangle. So it's really the same thing, but considered now in the category D. Okay. Now, suppose I have the situation that, say, Q of one such roof with W, F, and G, X, and Y is equal to another roof. So it's equal to the Q of some W prime, F prime, G prime, X and Y. So of course, in this computation, I assume that F and F prime are in the more C. Well, but this means that these two roofs are equivalent. So I can write a diagram. X, some Q in the middle, Y, so W, F, G. So here I have some W prime, F prime, and G prime. So the maps here I'm going to call S, T, U, and so there is such diagram, and since so then, since we know that the U is also in the more C, we can also notice that the S and T are also in the more C. So they standard business. Okay, so then I can, using condition A, I can say that, so by condition A, that is given in this lemma, I can say that there is a map which I'm going to call little m for the Q prime to the Q. So such that Q prime is in the subcategory A, and the composition of the U and M is in the more C prime. So, but then I can kind of take the same equivalence diagram, but I can pre-compose everything with the map M and replace this Q in the middle by the Q prime. So let me just draw another copy. Now in the middle I have this Q prime, and the maps are composition of the S and M, composition of the U and M. So then here we have composition of the V and M. So this is G prime. So now, so this is again a diagram that represents the equivalence of two rows. But now, since the vertex is in the A, so now this diagram makes sense in this category. So by looking at this, we can say that U is fatal. Right, so it's injective on the rows. Now I want to notice that this is full. Okay, so I wanted to formulate like this. If we replace the given roof, say with the W, F, and G, X and Y, by, again using assumption A with some W prime, map M to the W, so this is F. So I can consider a new roof, right? So where the vertex is W prime, and again the composition of the M and F, so this composition, say this is F prime, so F prime is still in the more C. So we can take any roof and represent it and replace it by this roof with the vertex from the A, and hence we can say that the functor Q is full. Okay, so finally the statement about reflecting the distinguished triangles. So assume that we have a diagram with the X, U, X, Y, Z with the maps U, V, X with a shift. So this is diagram in the category A modulo C prime. So such that, yeah, in this diagram I want to assume that the composition of the two morphisms, so V and U, this is 0. So I given a diagram with 6 objects, 6 maps, and I know that the composition of two morphisms is 0.
So we take a triangle.
Hmm?
So we take a triangle.
No, that's not a triangle.
Why not?
Well, because triangles are somehow are given in the triangulate structure. I'm not saying this is one of the distinguished triangles. So sometimes it's called the candidate triangles, where I have objects and the composition of two consecutive maps is 0.
What we are proving right now?
We're proving that the functor Q is reflecting distinguished triangles.
And so what does it mean? That it maps distinguished triangles to distinguished triangles?
No, it's what I was trying to explain earlier. It means that if I start with a diagram like this, I apply the functor, right? I get a distinguished triangle, then this means that this was a distinguished triangle. So let this be a diagram such that it becomes a distinguished triangle. So distinguished triangle in the D mod C. So the proof is actually a simple observation. So we extend U or complete U, maybe I usually say. So we complete U to a distinguished triangle, right? So we're given two objects and a map between them, so we can complete this to a distinguished triangle. And I want to show that the distinguished triangle is actually isomorphic to this kind of candidate triangle. So this is a distinguished triangle in the A modulo C prime. So it maps to a distinguished triangle. So this property is clear since the Q is a triangulated functor. So it maps to a distinguished triangle. So isomorphic to the image of this diagram. So call this star. Image of this star. So, and since Q is fully faithful, star is distinguished triangle. So actually this follows from the fact that we have a fully faithful functor.
That's just another.
Yeah. Okay, so so now I'm going to prove maybe the most important theorem of derived functors. So if the triangulated functor f from category D to category T is right, see, adaptable then it admits the right derived functor. So I'm proving only the statement for the right derived functors, but of course you can analyze everything and give a proof for the left derived functors. Okay, so in the proof, first of all, I want to fix notation for the adapted class. So A will be the right adapted class for F else. And the theorem essentially follows by analyzing the diagram. So I have this right adapted class, so this is, or right adapted subcategory. This is the same thing, so I have the embedding of this A into the D. So I also want to call the functor, so the quotient functor from the A to the A modulo C intersect this A point A. Now there is the quotient functor, which as usual I'm going to call Q from D to the D modulo C, and you already know that there is a functor here, which in this proof I want to call T. So T exists by the previous lemma because the second condition of the adaptability, as I mentioned before, implies the say condition A of the lemma. So that we have this T, and I also know that T is fully faithful. So T is fully faithful functor, and again, if you look at the condition T of the adaptability, it means that T is essentially surjective. So the observation is that the T is fully faithful by previous lemma, and previous lemma works because the second condition of adaptability implies the conditions of the lemma, and also by condition 2 adaptability, T is essentially surjective.
We should say it's by exercise from the assignment 1.
Yeah, no, I don't use this, but also follows. So T is essentially surjective, and this means that there is a functor that goes in the other direction, and I'm going to call this functor S. So the whole diagram that I have, I also have some category T somewhere, and there is functor F for this category T, and later we will introduce another function. It's the moment that what we have. So this S is just for this T. This is a functor that goes in the other direction, and we have two natural isomorphisms. So there is theta. This is the natural isomorphism. So what you can notice, so what's the meaning of this functor S? Actually, it takes an object and can replace this object by the object in the category A, then you can apply T back, and it's just an embedding of this quotient into this quotient. So S morally is, so S of X is a factorial resolution of X, which is an object in D. So this is the meaning, the essential meaning of this functor S. So why this is crucial for the computation. And there is a remark that actually the composition of S and T is not just isomorphic to the identity. This is just actually equal to the identity. not that important, I think, for the proof, but you can notice that the S and T is just the identity, right? Because when you compute S and T, right, you actually, well, you have something in the image of the T, right? So here you need the essential subjectivity, but since it's in the image, this is already kind of an object A, so you don't need to replace this by object equivalent to the object in A modulo the Morse C. So if you go with this, you don't do anything with the objects, and also you can morph it. So this composition is just the identity. Okay. Then I want to use the universal property, so by universal property of the quotient, so there is functor h from the A to the quotient of the C intersect A to the T. So there's functor h somewhere here. Right, and this exists. Well, first of all, this exists because the intersection of the C and A is contained in the kernel of the functor f composition with phi. Okay, so I have this functor, C intersect this A is in the kernel of this functor, right? Because this is condition 1 of the adaptability, right? That the intersection of C and A is in the kernel. Hence, by the universal property of this quotient functor, there is H. Or we can notice also, maybe later for the computations, we'll need that the Hj is the same as isomorphic to the Fi. And also, by looking at this diagram, we can also notice that the Qi is isomorphic to the Tj. Okay. So I want to take an isomorphism eta for the object x. So this is from the x to the t as q of x. So this is isomorphism in the quotient category, d mod c. So it is represented by some roof. Represented by a roof, so with the vertex. So I want to, in the roof, so the second kind, the vertex is w prime. There is a map from the x, I'm going to call this b prime, and the map from the y, map y from the t as q of x. Sorry, the map a prime. So here a prime is in the more C. So, but using condition 2, again, of the adaptability, we can claim that there is a morphism, I'm going to call this little e, from some w, from the w prime to some I of w. So this I of w is just a way to say that I have an object in the category A. I want to reflect this in the notation, I don't want to write this with words. So such that this E is in the more C. So I can take this roof and replace this by another roof, which is just, say, for the vertex I have I of the w, then there is w prime, this is E, x b prime, so there is new b, which is just this composition, and t as q of x, so there is this composition A. So in other words, without loss of generality, condition 2 allows me to think that the vertex is an object in the category A. So something that we used, well, similar arguments we used in the proof on the previous level. So, yeah, E is in the more C, since this is a composition of two maps in the more C. Okay, so the goal is to show that pair, well, essentially pair HS and some natural transformation, which I'm going to define a little bit later, is a right derived functor. So gamma will define later, but you can see that the H kind of hits the position of the S and H. So this is a functor from the quotient to the T. So this is defined in the right category, but for the computation and for the proof, it is more convenient instead of the HS to present this in a little bit different form.
And it's right direct functor of what function?
Okay, of course.
What
Okay.
is gamma?
Gamma we'll define later. So essentially I'm saying that there is a gamma that I'm going to define later such that this pair is a right functor. But before I do this, before I define gamma, I want to make a comment about this functor composition of the H and S. So first of all, this here is a little observation. If I take object X in the category D, and then for this object X, I can find an object Y in the category A, such that, quite formal computation by the way, SQX is equal to the J of Y, right? I can consider this in the quotient category of the D mod C, which is equivalent to the quotient of the A modulo C intersect with A. So, and since the objects here are the same as objects here, so clearly I have this trivial observation. So using this, I can take HSQ of X, and I can rewrite this, just using object Y that I just introduced, as the HJ of Y, and now using commutation, I can write this as the Fi of Y. And now this is a little bit silly step, so I can write this as an Fqi of Y, right? Since objects in these two categories are the same, right? It really doing just the same thing. I just kind of interpret this a little bit differently in which category this lives.
What is F?
F is a given functor, so we have this
Yeah,
one.
but F don't. It's just saying about objects, not about morphisms.
Yeah, so we kind of can work separately with objects and morphisms. And morphisms will be left as an exercise. So essentially, what I'm trying to achieve, I want to present this H and S a little bit differently, that at least makes sense for the objects. And this is very useful for the computations. So I can write it like this, and then, since I have this identity that the composition of Qi is the composition of the T and J, I can also write this as an F T J of Y, and finally again plug in definition of the Y and write this as an F T S Q of X. So on objects, instead of computing HSQ on the object X, I can compute this composition of the four functors. And the answer is the same. I'll explain a little bit later why this is a useful observation. Okay, so this is this, and now I want to define gamma. So we have this map A, which is a map from the TSQX to the I of W. Now, since this map A is in the more C, when I apply functor Q, I'll get an isomorphism of something invertible. So there is a map from the Qi of W, so Q of A inverse, which hits to the TSQ of X. Again, formally I need to write Q here, but this is already in the quotient category. So then I can start with the F of the W. Oh, formally I can present it like this, or just rewrite it this again in a silly way. This is this composition, Now I can apply functor f to the previous diagram, and I will get f of the q of A inverse, and this will be in the f. This will be in the f ft as q of x.
Okay, what's the first one? It's just
That was already.
I think you can.
So the first one is just f of the object W. And then there is a bunch of Fourier transformations just to make sense that this composition actually exists and makes sense as a composition from this object to this object. Okay, so then you define essentially gamma x as the composition of the f of A inverse, right, which is this map. So I can, this is definition of the f of A inverse with the f of B. So with more details, we have f of x, which is mapped with the f of B to the f of W, and then I take this composition on the previous line, and then we're just going to call this f of A inverse to the f t s q x. Okay. Now this is a way to define gamma using as a derived functor FTS. So essentially the idea of writing the composition of the FTS, since formally it doesn't make sense, the idea is to think about all objects that live inside the category D. It just depends what we can think isomorphism with the category. Or in other words, what I'm trying to do, I'm trying to take this natural isomorphism, right, which is a natural isomorphism in the quotient category, and leave this as a map in the category D. Well, this is a little bit problematic. You can do this directly, but you can do this with this line of arguments. So looking specifically at the vertex of the roof and do the silly computations. And actually you can save this. So there is a way to correct this. So there's another definition. So another definition of gamma, which is technically makes more sense, but it's a little bit harder. So another definition. So this kind of as a remark inside the roof. You can define gamma as the composition. So as before, f of the object s is mapped by the map f of b to the composition of the f of the I of W. Right? This is straightforward, but it's not possible to read this. So then, for this thing in the middle, you first of all can present this as the H composition with J, which I apply to W. And here, this makes sense. This is an honest interpretation that follows from the definition of H. Now, I can use the fact that I can write factor J as an S, Q, and I. Right, so this is isomorphic to the H, S, Q, I of W. That's the next step. So this identity obtained, remember that before we had the identity that the, right here, then erase later, I have QI was equal to the TJ. Right? I can just apply S to the both sides. Then there will be a composition of S and T, which is the identity. So it will be just J, and then the composition of S, Q, and I. So this is the next step in this computation. Now, here I can apply functor HS, which is applied to the Q of the A inverse. So Q of the inverse is the same map here. And this will hit us in the h s t s q of x. Not just a straightforward application of this, of the functor hs, composition hs to this arrow. And here, since the composition of the s and t is identity, we can simplify this and write this as just the composition of three functors h, s, q of x. So that's an alternative definition of the gamma. It's a little bit better because on every step the composition of the functors makes sense. There is no something called ft, like in the previous computation. But really what's going on here is that the gamma, natural transformation gamma, is functor f, which is applied to the eta, and you can leave this eta from the morphism in D mod C to the morphism in the D. That's the idea of the proof. So that's a natural transformation. Now let's show that this is a derived function. So show that FTS gamma or HS gamma, which is, as we agreed, the same thing, is the derived function. Well, for this, suppose I have another function. So there is a function g from the quotient category to the t, and there is a natural transformation. So let's call this rho. So rho is a natural transformation after the composition of the g and q. So suppose this data given. So I'm checking the definition of the right derived function. So I want to find the corresponding natural transformation, and I want to show that this natural transformation is unique.
It was HS. Why it's FTS now is right derived function?
Well, because as I explained, because I can think about this by this computation, that on the objects this is the same thing.
Okay.
So it is a little bit more convenient for the computations when I check this is derived function. Well, you can think about it as follows. So you can take this second line of computation as a definition of gamma, and this is a little bit more precise. And from this, for example, it follows that this is indeed a natural transformation that doesn't depend on the how you present this.
Mm-hmm.
But for objects, you can as well compute this with the FTS.
Mm-hmm.
And for the maps, you can carefully check that everything also works. When I'm going to check that this is actually derived function, I need to do some computations. And if I do computations with this definition of gamma, the computations become kind of very long and messy. And the computations which works only for the objects and they use FTS in the definition, these are very simple, straightforward computations. So I decided to, instead of doing some long computations for entire lecture, just present you what the idea for the proof is and work out for the objects and leave as an exercise that everything works out for the maps.
Mm-hmm.
Okay. So this now data is given, and now I want to define the. So we define natural transformation theta, which is going to be g function g applied to the eta sub x inverse, which makes sense since eta sub x is natural morphism. Composition with the rho on the object ts q of x. So that's a natural transformation from the f ts q x to the g of x. Okay. Now I'm using the fact that rho is given as a natural transformation to write the following commutative square. So I have f t s q x. So here this is rho TS QX, G TS QX. So there is gamma sub x, which is the f according to the theta x, f x, rho sub x, GQ x, and this is G over eta x. So that's the commutative square. So since this is a commutative square, well, you can notice that also this is the isomorphism, and there is a map in the other direction. And so there is a map in the other direction. And now if you look at the definition of the theta, wait, is this right? No, so, sorry, of course, in the other direction, sorry. Now this makes a little bit more sense. So now, if you go like this with the rho and then with this inverse map, that's by definition the theta, right? So this natural transformation is theta sub x, this natural transformation is gamma, and this is rho. So in other words, from this commutative diagram, I see the commutative triangle of natural transformations. So the gamma, rho, and this is f t s q, which are also the objects I identify with the h s q, and this last transformation is the composition of theta and we have a universal property that given kind of the functor, the derived functor, which is the pair of the gamma and this functor, and for any given rho and g, there is a unique natural transformation here. So what we obtain at the moment, that there is natural transformation here with this definition, but we don't know the theta prime. Natural transformation, so making the triangle star commutative. So let's take another such transformation. Well, in terms of formulas, maybe I can write this as the rho. Using that I have a natural transformation, I can write to the hs, if you just use the this is G of x, this is G T S Q of x, and the map is theta prime T S Q of x. So I'm just using that and also for the computations I want to write this as a formula. So G of the eta sub x composition with the theta prime x is theta prime T S Q of x H S of the eta sub x. So then eta of the objects TSQ of x, right? So that's the same thing, but for the different object, which is TSQ. Now I can use this formula with the rho theta q and gamma x but for the different object again. So I can write this as the theta prime TSQ of x. Two computations that we've done before, the commutativity of the square and commutativity of the triangle, but for the theta prime. Okay, but now I claim that when you compute this not on any object, but when you compute this on the object TSQ of x, this gamma, component gamma, is actually an isomorphism. So gamma TSQ of X is an isomorphism. Well, because if you return to the definition of the gamma, and since you know that the composition of the TSQ is an isomorphism, then the eta sub X, you can choose this to be just the identity. And when you leave the identity, you get, well, at least you get an isomorphism. Oh, well, you leave the identity, you get the identity, you apply the F, you get something that gives you an isomorphism. So that's an isomorphism for this object. And since this is an isomorphism, we can say that the composition of the G applied to the eta sub X and the theta prime sub X is equal to the theta prime TSQ of X. The composition with the HS of the eta sub X. Well, this is just this formula for the primes, right? But now I write something like this for the primes, but theta is also a natural transformation, so the same formula holds if I erase all the primes. So this will be, oh, okay, so let me just say it like this. Before I'll write this theta TSQ of X HS eta sub X, right? This is by the previous computations. Since I know that this is an isomorphism, I know that for the objects of the form TSQ of X, theta and theta prime are the same. So I can just take this formula and erase theta prime from the formula. And now for this part, I can also rewrite this with this part, since this is just the fact that the theta and theta prime are natural transformations, and they are both natural transformations. So this is G of the eta sub X, theta X. Okay, but that's the end of the computation, right? Because now I can cancel this from the left and from the right, because this is an isomorphism. And so I see that for any object X, these two natural transformations actually coincide. And that's the end of the proof of the theorem. Now, as you can see, there are some little problems with the proof. Well, namely that, for example, when you do computation like this, it doesn't exactly make sense, because you take compositional functors that are not composable if you just do straightforward computation. But this makes sense because we can work in the large category D, and you think about the errors with the category D and try to make this precise in this sense, try to make this exactly precise with this sense. But as you can see, for the computations here, it is much more convenient to have FTSQ, and for that computation it is convenient to have H and S. So I don't see how we can avoid this problem, or you can, as I said, you can try to do the following. You take this as a definition, and then you modify this computation. So you replace this with the HSQ and try to do this as a sequence of isomorphisms and still get the gamma. But the computation, at least when I try to do this, is quite messy and requires several workloads to write down. So I decided maybe to skip some and do this maybe a little bit, not exactly formal with this composition, but at least the computation makes sense immediately. Okay, so I want to, before I formulate the next theorem, I want to start with some setup. So I have a category D, functor from the category D to the category D prime. So then inside D and D prime, I have some subcategories. So C is a subcategory inside D, and there is subcategory C prime inside D prime. And I want to assume that this C prime is thick. this will be important for the computations. So then I have quotients. So there is a quotient factor Q of the D over C, and there is a quotient factor Q prime of the D prime modulo C prime. So then there is another factor G, so then we have category T. And then we can talk about the derived functors. So the derived functor for the G will be a functor from the quotient category to the T. And the derived functor now, I want derived functor for the composition of the Q prime and the F. So this will be a derived functor that lives here. So my derived functor of the composition Q prime F. So I assume that these two derived functors exist. So that the right derived functor of the composition with some natural transformation theta and the right derived functor for the functor G with natural transformation omega, so exists. So then we have another natural transformation mu. So mu is a natural transformation from the composition of the G and F. So you take natural transformation omega, take a composition with the functor F. So this will be to the R G Q prime F. And then here you take a composition of the RG and the natural transformation theta. So this will be to the R G R Q prime F and Q. So since we have this natural transformation, if there is a right functor for the composition of the G and F, so C for the natural transformation, so then there is a unique natural transformation gamma from the right functor of the composition of the G and F to the composition of the derived functors. Right derived functor of the composition and the composition of the right functors. And so here, to make sense of the composition of the derived functors, I need to take the right derived functor of this composition of the F and Q prime. Otherwise, it doesn't make sense. And now I have a bunch of assumptions. I have an assumption that there is three derived functors. So the derived functor for the Q prime and F, derived functor for the G, and also I assume that there is a derived functor for the composition. So with these assumptions, I can, the universal property gives me that there is a unique natural transformation gamma. So in the theorem, I want to see what conditions are enough to conclude that the gamma is an isomorphism. So when I have this natural property that the composition of the two derived functors, the derived functor of the composition is the composition of the derived functors. So in the theorem, I have assumptions, so assume that first of all A in the D is the right adapted for the composition Q prime F and the subcategory C. So A prime in the D prime is right adapted for the second functor, for the G. So right adapted for G and C prime. So if additionally I know that F of the A is contained in the A prime, so I have adapted objects to the adapted objects. So then gamma is a trinatural isomorphism. Or in other words, the derived factor of a composition is the composition of derived factors. Okay, so the proof is a little bit more elementary than the previous one, definitely shorter. Okay, so I start with some observations. So suppose I take the composition of the Q prime and F and apply this to the intersection of the C and A. So what we can say about what happens if I apply this composition of factors to the intersection of the C and A?
Well, first when it goes to C prime, it's 0, something like that.
Yeah, so the answer that this composition is 0. And why this is 0?
Well, if it lies in A,
Yeah, by the assumption this is.
just
So f of A lies in the A prime, right?
no, it's
No, because
Yeah.
A is adapted for prime then.
Yeah.
so we need to know that C intersect with A lies in C prime.
Well, we know that the C intersect A since A is adapted for the C and for the F. This is in the kernel of the functor F, right? So if you apply this composition, you get 0.
Well, it's a kernel of functor F.
F, yes. F of the C intersect with A, right? So this is something in the okay. Now, since I know that the F of the A is contained in the A prime, and I have this observation that the intersection is contained in the C prime, I can make a conclusion that the F of the intersection is contained in the intersection of the C prime and A prime. Right?
Yes.
But then, from this, the intersection of the C and A is in the kernel of the composition of functors G and F.
Mhm.
But if this is the case, we can say that they adapted for the composition of functors G and F. So there is a derived functor for the composition. Okay, so this is the first observation, and the second observation, well, the second part of the computation is the following. I can choose these functorial resolutions, so choose S from the D mod C to the A mod C intersect with A, and S prime from the D prime modulo C prime to the A prime modulo the C prime intersect with the A prime. So this is as in the previous theorem. So I can use these functorial resolutions to define derived functors, for example, for the derived functor of the G and derived functor of the composition Q prime and F, with these functorial resolutions, precisely as in the proof of the previous theorem. Okay, so then if I use this, I can also understand the gamma sub x explicitly. So for x, which is an object in the A, I can say that I have the following. If I take the derived functor of the composition and compute this on the x. Notice that it's important that x is in the A. So what I can say about this?
Can you recall what is gamma x?
Gamma x, well, this is what exists just by the universal property. But I want to understand this gamma x precisely, since I have a precise definition of the derived functors using these functors s and s prime. And now, now I also want to take object in the category A.
Suppose it should be just gf of x.
Yeah, that's right, because this follows just from the construction of the derived functor. If you construct derived functor using this adaptable class, and you take an object from the adaptable class, then the derived functor on this functor is the same as the original functor. This is especially clear if you use FTS as a definition. So this is the composition of the two functors that I compute on the object x. And now I use this argument 2 more times. I can write this as the right derived functor of g, composition with the functor f applied to the object x, and also as the composition of the two derived functors applied to the object x. So the same kind of ideas, but now for the two functors independently, separately. So we can see that since we have this assumption that f of a is lies in the A prime, that for any x in the A, the derived functor of the composition is actually a composition of the derived functors. So now we want to extend everything using resolutions to any object in the category D. And this is done, say, by looking at the natural, or the commutative square that comes from the natural transformation. So I have our gf applied to the x. So here this is gamma x prime f of x. Now this is derived functor applied to the eta x. The same eta x as before, so I may write it later. So this is to the r gf tsx, no, tsqx. But well, q doesn't do anything, so I can as well write tsx. So this is gamma dsq of x. Okay. So this eta sub x is as before the isomorphism in the D mod C for the. So I can take this map and apply, take this map and use the fact that the gamma is a natural transformation, get this commutative square, and in this commutative square we can notice several things. So first of all, we already know that this is kind of the replacement of the object x by its resolution, which is an object in A, right? So we know that what I want to show since. Yeah, I want to show that for any object x, this is an isomorphism, right? I know that for object which is in the subcategory A, I have here an isomorphism. So this is an isomorphism. Now, this map in the quotient category is also an isomorphism, right? And this is a functor which is applied to an isomorphism, so that's an isomorphism. And the same is here also, right? Because I have an isomorphism and I apply some functor to the isomorphism, I still get an isomorphism. So the gamma x for any x in the which is an object in D is an isomorphism. Okay, so this is the composition. Now, definition. So suppose we have a function, so f from the D to T is a triangulate function. Now C in the D is a triangulated subcategory. So x in the D, some object is called right acyclic if so right acyclic with respect to the f and c. Right acyclic for functor f and the given subcategory C. So if we have the following property, for any map, say S, from the X to the Y, which is a map, again, in the more C, such that the composition, so the functor f applied to the composition is an isomorphism. So, and the notation, so A with the indices F and C, this is the full subcategory. Of acyclic objects for F and C. So I think this is quite interesting definition because I define the notion of acyclic objects without using the derived functor. Right? So probably the standard definition that you already know is the following. You say, at least for the abelian categories, you say that object in abelian category is acyclic if the derived functors for some functor f, if the derived functors are zero on this object, right? But for this you need to know that derived functor is this. And in this definition, where you just use the functor f to say that the object is acyclic, which kind of makes a little bit more sense since we want to use acyclic objects to construct resolutions and show that there is a derived functor. But later we will see that this definition is equivalent to the standard definition, namely object is acyclic if and only if functor coincides with the derived functor of this object. Okay, so first lemma. So object x in the D is in the right orthogonal complement, so right orthogonal to the C, if and only if x is right acyclic for any functor f from D to some other triangulate categories. So if we think, and we will see that this works, that the acyclic objects is the objects that we kind of use for resolutions, and then the right orthogonal is the place where you can find resolution for any functor. to the category C. Right, so then for a map S from the X to the Y in the more C, so there is map T from the Y to the Z such that the composition is actually equal to 1. So how to show that this is true? Well, I think this was from the lemma that we proved when we discussed the right orthogonals for the subcategories. If there was a lemma, so this is the right orthogonal.
I have shown that every map in Morse is a section.
Yeah, thank you. I was thinking about the different lemma. So the lemma which with 4 equivalent conditions,
Yes.
right? So first condition was that the x that's the right orthogonal, and the condition 4 was exactly what I have here. Yes. So this was from that lemma, and I was thinking about the different lemma. Okay, so this follows by that lemma in one direction, but in the other direction, so in the other direction, I can take as a functor f to be just the identity functor. So that's the functor from the D to the D. So then, for any map S from the X to the Y, which is in the more C, we can say, well, since this is acyclic, so there is T from the Y to the Z, such that now this composition T and S is an isomorphism. Well, and then this immediately follows that S is a section, and that, again, using the same lemma, we can conclude that the X is in the right orthogonal to the C. Okay, proposition, probably the last thing that I can do today. This full subcategory of acyclic objects for functor and subcategory C, well, this is a triangulated category, so triangulated subcategory, and also if you take the intersection of the C and the acyclic objects for the F and C, this is in the kernel of the functor F. Proof? Well, first of all, I think it is clear that this subcategory is closed under translations. So now let me assume that I have a distinguished triangle. So X, Y, Z, x with a shift is a distinguished triangle. And two objects. It will be convenient for me that the objects are y and z are in this subcategory. So I want to show, so the goal, what I want to show is that for the map S from the x to some object q in more C, well, there is some other object, there is some other map, there is T from the Q to the, I don't know, Q prime maybe, such that F applied to the composition is isomorphism. So we're going to check this construction several distinguished triangles step by step. So first of all, I start with a given distinguished triangle. Right? So then there is a given map S to the Q, right? And then I can form a homotopy Cartesian square. So here, so let's call this map T. So I don't know, maybe to indicate this homotopy Cartesian, I'll write something like this, but this is really symmetric. Right? So we take homotopy Cartesian square. And then there was a lemma I think in the second chapter, that whenever you have such diagram where you have a distinguished triangle, you have a homotopy Cartesian square, you can extend this lower part to a new distinguished triangle, let's call this object Z, in such a way, well, that this third map is just an identity. Okay? So agree with that? I'm using the lemma that if you have a distinguished square, you have homotopy Cartesian square, you can also extend this lower, so this map to another distinguished square, such that here I can put the identity. This is the lemma that we put before. Okay. So now I do the following. I take morphism T prime, right? So T prime to some object, also T prime, large T. So this is right here. So T prime is a map from the T to the T prime, which is also in the morph C, and such that f of the T prime T is isomorphism. Right? I can do this since I know that the object Y is not the A of C. So this is this. Now, again, I do the same step. I take this diagram and I construct the homotopy Cartesian square. So I'll get some Z prime, and I'll get some map Q. Okay, so in this case, I take this map between T prime and Z prime and also extend this to a distinguished triangle. So I call this Q prime, and then there is a Q prime with a shift. And yeah, so then there is a map S prime here. S prime is a shift. So what are the claims?
How we get the lower triangle?
Well, I constructed this homotopy Cartesian square.
Yes.
I take this map and just complete this to a distinguished triangle.
So how we get the map from T prime to Z prime?
From T to
So
I start with the part of the diagram that is given. So this part is given.
yes.
So I construct the homotopy square, homotopy Cartesian square.
The second square is also homotopy Cartesian.
Yes. So on each step, I compute the homotopy Cartesian square. So then I'll get this middle of the diagram, so I'll get this map, and I complete this pre-distinguished triangle.
Yes.
Which one is homotopy Cartesian square?
This one,
Why? So
by definition. Well, I'm having this distinguished triangle. I have a map T prime, which is this, like that thing. So I have this part of the diagram. I can complete this to homotopy Cartesian square. I do this.
so we completed.
Exactly as in the previous step, right? Because in the previous step, I was given the map S, and I completed this to homotopy Cartesian
Okay.
square first of all.
Mhm.
I do this on the second row also. Yeah, and there are things that I can notice, and I didn't notice in the beginning. So since S is in the more C, right? And I take the homotopy Cartesian square, T is also in the more C, right? That was a property that we proved for homotopy Cartesian squares. And this is what I use here. So the T is in the more C. And the same works here. So I choose T prime to be in the more C, right? But since I take a homotopy Cartesian square, this map Q is also in the more C. And then there was a lemma that if in the map between two distinguished triangles, there are two maps from the more C, the third map I can also choose from the more C. So this map S prime that I constructed is in the more C. Okay.
That's the finish.
Hmm?
That's all.
No, I don't think so. We need to continue this. So I didn't use another step with the Q prime here. Right, so I can choose the Q prime. So say to the Z double prime. So Q prime from the Z prime to the Z double prime. This is in the more C, such that the composition of the Q prime and Q when I apply factor F give me the isomorphism. Okay. So the same thing as before. I have this part of the diagram, so it's kind of Z prime in the middle of these two arrows, and I compute the homotopy Cartesian square. So there will be some object Q double prime with a shift. So I'm going to call it like this. So then here they will be mapped. So here they will be mapped S double prime with a shift. So hence they will be mapped S double prime without a shift to the Q prime. So there will be T prime, 1, and Z prime. So kind of rotated version of the same argument that I used before. If I have two distinguished triangles and I have homotopy Cartesian square, I can when I complete the lower distinguished triangle, well back in the lower part of the diagram to distinguished triangle, I can do this in such a way that this map is the identity.
Why it's 1? Yeah, okay, repeat.
Again, this is the lemma that we had before, that if you have a distinguished triangle, homotopy Cartesian square,
Yeah.
you can extend this map in the bottom part to distinguish triangles such that we have an identity here. Okay, now I think that's the whole diagram that I need to finish the proof. So I just need to calculate what I have. What I have here is this composition, which is really just the composition of these two maps, and this composition, which is just the composition of these two maps, right? And when I apply F to these two compositions, I get the isomorphism. Hence, when I apply F to this composition, I get the isomorphism. So, by looking at the diagram, F applied to the composition of the S double prime, S prime, and S is isomorphism. Right? But that exactly means, and then the object X is in the AFC. I constructed the map, said that the composition is isomorphism. Now I can construct this in 2 steps, but I take this composition, and that's what I need in the definition. Okay, and the last part So I need to show that the intersection is in the kernel of the functor f. So for the last part, let me take x, which is in the C, intersect with the A, FC. Okay, so then I claim that if I look at the map from the x to the 0, this is in the morph C.
C, that means that cone of it also on line C.
Yeah. Yeah.
Since C is just a triangle, subcategory.
Yeah, or you can say you can complete this to distinguish triangle, then you get x, right?
Yeah, that's
So which also is. So this is in the morph C. So, okay, so since this is in the morph C, then well, the first observation, if you apply functor f to this object x, right, then you'll get a 0 thing, and then you can kind of find, well, this is a very trivial argument with the zeros. You can find another map, right, such that when you take a composition with another map, you'll get an isomorphism, right? Even at yf, you get an isomorphism. So then some other map to the y. So then this composition